Greetings everyone, I am Fatima, research scholar. My research supervisor is Dr. S.G. Venkatesh. My research work is titled Development of an Extreme Learning Mission Technique for a Class of Fractional Differential Equations in Caputo. My research focuses on developing an efficient numerical approach for solving fractional differential equations using an extreme learning mission framework with the fractional order shifter legendre polynomials. In this video, I will give a brief overview of the motivation behind the work, the proposed methodology, the major results, and the key features of the developed framework. Fractional differential equations are useful for modeling systems that exhibit memory and hereditary effects, and they arise in many real-world applications. Due to the complexity and non-local nature of fractional differential equations, conventional numerical methods can become computationally demanding, especially for nonlinear and high-dimensional problems. In recent years, machine learning-based methods have emerged as an alternative approach for solving differential equations. Among these, neural network-based methods are particularly attractive because they can approximate the solution without requiring a conventional math-based discretization. One such approach is the Extreme Learning Machine or ELM, which offers fast training by analytically determining the output weights. Motivated by these advantages, the main objective of my research is to develop an efficient numerical technique for solving fractional differential equations using an ELM framework based on the fractional order shifter legendre polynomials. The study mainly considered five classes of fractional differential equations: fractional ordinary differential equation, system of fractional ordinary differential equation, time fractional PDE, space fractional PDE, and space-time fractional PDEs. The proposed methodology consists of several steps. First, the domain of the considered problem is discretized into equally spaced points to generate the training dataset. Second, the neural network trial solution is constructed using FSLPs as the hidden layer activation functions. The approximate solution is expressed as a linear combination of these basis functions, but the corresponding output coefficients are the unknown parameters. Next, this trial solution is substituted into the given FDE along with the required initial and boundary conditions. This transforms the original differential equation into a system of algebraic equation for the unknown output coefficient. For linear FDE, the resulting system is linear and can be solved directly using the Moore-Penrose pseudo-inverse. Thus, the output weights are obtained analytically without requiring an iterative training procedure. For nonlinear FDE, the resulting system is nonlinear. In this case, the NLSQ-Pertup algorithm is employed to determine the unknown output coefficients. Finally, the computed coefficients are substituted back in the trial solution to obtain the approximate solution of the FDE. A key contribution of this study is the systematic development of activation functions specifically designed for the different classes of FDEs. For fractional ordinary differential equation and their systems, the activation functions are constructed using FSLPs. For time fractional and space fractional PDEs, a hybrid activation function is introduced by combining fractional order shifter legendre polynomials with the classical integer order polynomial functions. In time fractional case, the temporal variable is approximated using fractional order shifter legendre polynomials, while the space variables is represented using classical integer order polynomials. Conversely, for space fractional problems, the spatial variable is approximated using FSLPs, while the temporal variable is represented using the classical integer order polynomials. This hybrid formulation allows fractional and integer order components of the governing equations to be approximated appropriately. This also leads to enhanced sparsity of the operational matrices, reduced storage requirements, and improved computational efficiency. For space-time fractional partial differential equation, a two-dimensional formulation of the fractional order shifter legendre polynomial is employed as the activation function. Another important feature of the proposed framework is that the hidden layer weights and biases are fixed at 1 and 0 respectively. Therefore, it reduces the cost of computation and training. Overall, the proposed approach combines the approximation capability of FSLPs with the computational efficiency of the ELM framework to obtain numerical solutions of different classes of fractional differential equations. In addition to the numerical study, the study also includes a theoretical analysis. Before applying the proposed method, the existence and uniqueness of solution of the considered FDEs are established. The convergence and stability of the proposed numerical scheme are also investigated along with its computational complexity. Finally, extensive numerical experiments are conducted to validate the proposed method. The computer approximate solutions are compared with the corresponding exact solutions, and the absolute error, maximum absolute error, residual error, and the effect of number of neurons on solution accuracy are also investigated. Overall, the proposed FSLP ELM framework provides a mesh-free, computationally efficient, and flexible approach for obtaining numerical solutions of FDEs in the Caputo sense. Thank you all for patiently listening to this presentation.